Polygon.
In geometry, a polygon/polygon/ is traditionally a plane figure that is bounded by a finite chain of straight line segments closing in a loop to form a closed chain or circuit. These segments are called its edges or sides, and the points where two edges meet are the polygon's vertices or corners. The interior of the polygon is sometimes called its body. An n-gon is a polygon with n sides. A polygon is a two-dimensional example of the more general polytope in any number of dimensions. The word polygon derives from the Greek polis, much, many, and gonia, corner, angle, or gnu, knee. The basic geometrical notion has been adapted in various ways to suit particular purposes. Mathematicians are often concerned only with the bounding closed polygonal chain and with simple polygons which do not self-intersect, and they often define a polygon accordingly. A polygonal boundary may be allowed to intersect itself, creating star polygons. Geometrically, two edges meeting at a corner are required to form an angle that is not straight, 180 deg. Otherwise, the line segments may be considered parts of a single edge. However, mathematically, such corners may sometimes be allowed. These and other generalizations of polygons are described below.
Classification. Number of sides.
Polygons are primarily classified by the number of sides. See table below.
Convexity and types of non-convexity.
Polygons may be characterized by their convexity or type of non-convexity. Convex, any line drawn through the polygon, and not tangent to an edge or corner, meets its boundary exactly twice. As a consequence, all its interior angles are less than 180 deg. Equivalently, any line segment with endpoints on the boundary passes through only interior points between its endpoints. Non-convex, a line may be found which meets its boundary more than twice. Equivalently, there exists a line segment between two boundary points that passes outside the polygon. Simple, the boundary of the polygon does not cross itself. All convex polygons are simple, concave, non-convex and simple. There is at least one interior angle greater than 180 deg, star-shaped, the whole interior is visible from a single point, without crossing any edge. The polygon must be simple, and may be convex or concave, self-intersecting, the boundary of the polygon crosses itself. Branko Grünbaum calls these coptic, though this term does not seem to be widely used. The term complex is sometimes used in contrast to simple, but this usage risks confusion with the idea of a complex polygon as one which exists in the complex Hilbert plane consisting of two complex dimensions. Star polygon, a polygon which self-intersects in a regular way.
Miscellaneous.
Equiangular, all its corner angles are equal. Cyclic, all corners lie on a single circle, called the circumcircle. Isogonal or vertex transitive, all corners lie within the same symmetry orbit. The polygon is also cyclic and equiangular. Equilateral, all edges are of the same length. A polygon with 5 or more sides can be equilateral without being convex. Tangential, all sides are tangent to an inscribed circle. Isotoxal or edge transitive, all sides lie within the same symmetry orbit. The polygon is also equilateral and tangential. Regular, the polygon is both cyclic and equilateral. Equivalently, it is both equilateral and equiangular. A non-convex regular polygon is called a regular star polygon. Rectilinear, a polygon whose sides meet at right angles, that is, all its interior angles are 90 or 270 degrees, monotone with respect to a given line L, if every line orthogonal to L intersects the polygon not more than twice.
Properties.
Euclidean geometry is assumed throughout.
Angles.
Any polygon, regular or irregular, self-intersecting or simple, has as many corners as it has sides. Each corner has several angles. The two most important ones are interior angle, the sum of the interior angles of a simple n-gon is n. 2, p radians or n. 2, 180 degrees. This is because any simple n-gon can be considered to be made up of two triangles, each of which has an angle sum of p radians or 180 degrees. The measure of any interior angle of a convex regular n-gon is radians or degrees. The interior angles of regular star polygons were first studied by Poinsett, in the same paper in which he describes the four regular star polyhedra. For a regular gon, a p-gon with central density q, each interior angle is radians or degrees. Exterior angle, tracing around a convex n-gon, the angle turned at a corner is the exterior or external angle. Tracing all the way around the polygon makes one full turn, so the sum of the exterior angles must be 360 deg. This argument can be generalized to concave simple polygons, if external angles that turn in the opposite direction are subtracted from the total turned. Tracing around an n-gon in general, the sum of the exterior angles, the total amount one rotates at the vertices, can be any integer multiple d of 360 deg, for example 720 deg for a pentagram and 0 deg for an angular 8, or antiparallelogram, where d is the density or starriness of the polygon. See also orbit, dynamics. The exterior angle is the supplementary angle to the interior angle. From this the sum of the interior angles can be easily confirmed, even if some interior angles are more than 180 deg, going clockwise around, it means that one sometime turns left instead of right, which is counted as turning a negative amount. Thus we consider something like the winding number of the orientation of the sides, where at every vertex the contribution is between 1/2 and 1/2 winding.
Area and centroid. Simple polygons.
The area of a polygon is the measurement of the two-dimensional region enclosed by the polygon. For a non-self-intersecting, simple, polygon with n vertices, the area and centroid are given by. To close the polygon, the first and last vertices are the same, that is, xn, n equals xo, yo. The vertices must be ordered according to positive or negative orientation, counterclockwise or clockwise, respectively. If they are ordered negatively, the value given by the area formula will be negative but correct in absolute value, but when calculating the signed value of, which in this case is negative, should be used. This is commonly called the surveyor's formula. The area formula is derived by taking each edge AB, and calculating the signed area of triangle AB with a vertex at the origin O, by taking the cross product, which gives the area of a parallelogram, and dividing by 2. As one wraps around the polygon, these triangles with positive and negative area will overlap, and the areas between the origin and the polygon will be cancelled out and summed to 0, while only the area inside the reference triangle remains. This is why the formula is called the surveyor's formula, since the surveyor is at the origin. If going counterclockwise, positive area is added when going from left to right and negative area is added when going from right to left, from the perspective of the origin. The formula was described by Meister in 1769 and by Gauss in 1795. It can be verified by dividing the polygon into triangles, but it can also be seen as a special case of Green's theorem. The area A of a simple polygon can also be computed if the lengths of the sides, A1, A2, and then the exterior angles, TH1, TH2, THN are known. The formula is. The formula was described by Lobschitz in 1963. If the polygon can be drawn on an equally spaced grid such that all its vertices are grid points, Pick's theorem gives a simple formula for the polygon's area based on the numbers of interior and boundary grid points. In every polygon with perimeter P and area A, the isoperimetric inequality holds. If any two simple polygons of equal area are given, then the first can be cut into polygonal pieces which can be reassembled to form the second polygon. This is the Bolyai-Gerwin theorem. The area of a regular polygon is also given in terms of the radius r of its inscribed circle and its perimeter P by. This radius is also termed its apothem and is often represented as a. The area of a regular n-gon with side s inscribed in a unit circle is The area of a regular n-gon in terms of the radius r of its circumscribed circle and its perimeter P is given by the area of a regular n-gon, inscribed in a unit radius circle, with side S and interior angle th can also be expressed trigonometrically as the sides of a polygon do not in general determine the area. However, if the polygon is cyclic, the sides do determine the area. Of all n-gons with given sides, the one with the largest area is cyclic. Of all n-gons with a given perimeter, the one with the largest area is regular, and therefore cyclic.
Self-intersecting polygons.
The area of a self-intersecting polygon can be defined in two different ways, each of which gives a different answer. Using the above methods for simple polygons, we discover that particular regions within the polygon may have their area multiplied by a factor which we call the density of the region. For example, the central convex pentagon in the center of a pentagram has density 2. The two triangular regions of a cross-quadrilateral, like a figure 8, have opposite sign densities, and adding their areas together can give a total area of 0 for the whole figure. Considering the enclosed regions as point sets, we can find the area of the enclosed point set. This corresponds to the area of the plane covered by the polygon, or to the area of a simple polygon having the same outline as the self-intersecting one, or, in the case of the cross-quadrilateral, the two simple triangles.
Degrees of freedom.
An n-gon has two n degrees of freedom, including 2 for position, 1 for rotational orientation, and 1 for overall size, so 2n. 4 for shape. In the case of a line of symmetry, the latter reduces to n. 2. Let k. 2. For an n-gon with k-fold rotational symmetry, ck, there are 2n. 2 degrees of freedom for the shape. With additional mirror image symmetry, dk, there are n. 1 degrees of freedom.
Product of distances from a vertex to other vertices of a regular polygon.
For a regular n-gon inscribed in a unit radius circle, the product of the distances from a given vertex to all other vertices equals n.
Generalizations of polygons.
In a broad sense, a polygon is an unbounded, without ends, sequence or circuit of alternating segments, sides, and angles, corners. An ordinary polygon is unbounded because the sequence closes back in itself in a loop or circuit, while an ppʒlɪɡ̒n, infinite polygon, is unbounded because it goes on forever. The modern mathematical understanding is to describe such a structural sequence in terms of an abstract polygon which is a partially ordered set, perset, of elements. The interior, body, of the polygon is another element, and, for technical reasons, so is the null polytope or nullitope. A geometric polygon is a realization of the associated abstract polygon. This involves some mapping of elements from the abstract to the geometric. Such a polygon does not have to lie in a plane, or have straight sides, or enclose an area, and individual elements can overlap or even coincide. For example, a spherical polygon is drawn on the surface of a sphere, and its sides are arcs of great circles. A digon is a closed polygon having 2 sides and 2 corners. 2 opposing points on a spherical surface, joined by 2 different half-great circles, produce a digon. Tiling the sphere with digons produces a polyhedron called a hosohedron. 1 great circle with 1 corner point added, produces a monogon or henigon. Other realizations of these polygons are possible on other surfaces, but in the Euclidean, flat, plane, their bodies cannot be sensibly realized. The idea of a polygon has been generalized in various ways. A short list of some degenerate cases, or special cases, comprises the following. Digon, interior angle of 0 deg in the Euclidean plane. See remarks above regarding the sphere, interior angle of 180 deg, in the plane. This gives an ppʒlɪɡ̒n, see below. On the sphere a dihedron, a skew polygon does not lie in a flat plane, but zigzags in 3, or more, dimensions. The Petrie polygons of the regular polyhedra are classic examples. A spherical polygon is a circuit of sides and corners on the surface of a sphere. An ʻpʒlɪɡ�n is an infinite sequence of sides and angles, which is not closed but it has no ends because it extends infinitely. A complex polygon is a figure analogous to an ordinary polygon, which exists in the complex Hilbert plane.
Naming polygons.
The word polygon comes from late Latin polygonum, a noun, from Greek polygonon, polygonon, noun use of neuter of polygonos, polygonos, the masculine adjective, meaning many-angled. Individual polygons are named, and sometimes classified, according to the number of sides, combining a Greek-derived numerical prefix with the suffix gon, for example pentagon, dodecagon. The triangle, quadrilateral or quadrangle, and n-gon are exceptions. For large numbers, mathematicians usually write the numeral itself, for example 17-gon. A variable can even be used, usually n-gon. This is useful if the number of sides is used in a formula. Some special polygons also have their own names. For example, a regular star pentagon is also known as the pentagram.
Constructing higher names.
To construct the name of a polygon with more than 20 and less than 100 edges, combine the prefixes as follows. The chi is not always used. Opinions differ on exactly when it should, or need not, be used, see also examples above. Alternatively, the system used for naming the higher alkanes, completely saturated hydrocarbons, can be used. This has the advantage of being consistent with the system used for 10 through 19-sided figures. That is, a 42-sided figure would be named as follows. And a 50-sided figure. But beyond decagons and dodecagons, professional mathematicians generally prefer the aforementioned numeral notation. For example, MathWorld has articles on 17 gons and 257 gons. Exceptions exist for side counts that are more easily expressed in verbal form.
History.
Polygons have been known since ancient times. The regular polygons were known to the ancient Greeks, and the pentagram, a non-convex regular polygon, star polygon, appears on a crater by Aristonothos, found at Kir and dated to the 7th century BC, and now in the Capitoline Museum. Non-convex polygons in general were not systematically studied until the 14th century by Thomas Bradwardine. In 1952, Geoffrey Colin Shepherd generalized the idea of polygons to the complex plane, where each real dimension is accompanied by an imaginary one, to create complex polygons.
Polygons in nature.
Numerous regular polygons may be seen in nature. In the world of geology, crystals have flat faces, or facets, which are polygons. Quasicrystals can even have regular pentagons as faces. Another fascinating example of regular polygons occurs when the cooling of lava forms areas of tightly packed hexagonal columns of basalt, which may be seen at the Giant's Causeway in Ireland, or at the Devil's Pass Pile in California. The most famous hexagons in nature are found in the animal kingdom. The wax honeycomb made by bees is an array of hexagons used to store honey and pollen, and is a secure place for the larvae to grow. There also exist animals who themselves take the approximate form of regular polygons, or at least have the same symmetry. For example, sea stars display the symmetry of a pentagon or, less frequently, the heptagon or other polygons. Other echinoderms, such as sea urchins, sometimes display similar symmetries. Though echinoderms do not exhibit exact radial symmetry, jellyfish and comb jellies do, usually fourfold or eightfold. Radial symmetry, and other symmetry, is also widely observed in the plant kingdom, particularly amongst flowers, and, to a lesser extent, seeds and fruit, the most common form of such symmetry being pentagonal. A particularly striking example is the starfruit, a slightly tangy fruit popular in Southeast Asia, whose cross-section is shaped like a pentagonal star. Moving off the Earth into space, early mathematicians doing calculations using Newton's law of gravitation discovered that if two bodies, such as the Sun and the Earth, are orbiting one another, there exist certain points in space, called Lagrangian points, where a smaller body, such as an asteroid or a space station, will remain in a stable orbit. The Sun-Earth system has 5 Lagrangian points. The two most stable are exactly 60 degrees ahead and behind the Earth in its orbit. That is, joining the center of the Sun and the Earth, and one of these stable Lagrangian points forms an equilateral triangle. Astronomers have already found asteroids at these points. It is still debated whether it is practical to keep a space station at the Lagrangian point. Although it would never need course corrections, it would have to frequently dodge the asteroids that are already present there. There are already satellites and space observatories at the less stable Lagrangian points.
Polygons in computer graphics.
A polygon in a computer graphics, image generation, system is a two-dimensional shape that is modeled and stored within its database. A polygon can be colored, shaded and textured, and its position in the database is defined by the coordinates of its vertices, corners. Naming conventions differ from those of mathematicians. A simple polygon does not cross itself. A concave polygon is a simple polygon having at least one interior angle greater than 180 deg. A complex polygon does cross itself. Use of polygons in real-time imagery. The imaging system calls up the structure of polygons needed for the scene to be created from the database. This is transferred to active memory and finally, to the display system, screen, TV monitors etc. so that the scene can be viewed. During this process, the imaging system renders polygons in correct perspective ready for transmission of the processed data to the display system. Although polygons are two-dimensional, through the system computer they are placed in a visual scene in the correct three-dimensional orientation so that as the viewing point moves through the scene, it is perceived in 3D. Morphing, to avoid artificial effects at polygon boundaries where the planes of contiguous polygons are at different angle, so-called morphing algorithms are used. These blend, soften or smooth the polygon edges so that the scene looks less artificial and more like the real world. Mesh polygons. The number of mesh polygons, meshed is like a fish net, can be up to twice that of freestanding unmeshed polygons, particularly if the polygons are contiguous. If a square mesh has n+1 points, vertices, per side, there are n² squares in the mesh, or 2n² triangles since there are two triangles in a square. There are n+1, 2/2, n2, vertices per triangle. Where n is large, this approach is 1/2. Or, each vertex inside the square mesh connects 4 edges, lines. Polygon count. Since a polygon can have many sides and need many points to define it, in order to compare one imaging system with another, polygon count is generally taken as a triangle. When analyzing the characteristics of a particular imaging system, the exact definition of polygon count should be obtained as it applies to that system, as there is some flexibility in processing which causes comparisons to become non-trivial. Vertex count. Although using this metric appears to be closer to reality, it still must be taken with some salt. Since each vertex can be augmented with other attributes, such as color or normal, the amount of processing involved cannot be trivially inferred. Furthermore, the applied vertex transform is to be accounted, as well topology information specific to the system being evaluated, as post-transform caching can introduce consistent variations in the expected results. Point-in-polygon test. In computer graphics and computational geometry, it is often necessary to determine whether a given point P equals XO, YO, lies inside a simple polygon given by a sequence of line segments. It is known as the point-in-polygon test.